Okay, can you hear me?
Yes, sir.
Yes. Yes, sir.
Okay. Um, can you see my screen?
Yes, sir.
Yes, sir.
Okay.
Yes.
All right. So today we're going to look at per unit systems. Okay. And if time permits, we will take a look at voltage regulation and efficiency. All right. So starting with per unit system, but before we start, I received some of your assignments. Some of you submitted very late. And some of the assignments, when I received them, I only have PDF. The code is not attached. Some have the code in the PDF, but they didn't discuss the results. Some were busy giving me a preliminary, telling me about transformers and what have you, before they dive in to start addressing the assignment. So I think this is what we will do. I will give you a template, okay, for the assignment solution, so that you see how you're supposed to answer the assignment, and maybe you can use that as a reference for your future assignment submissions. And for those who submitted their assignments late, some have excuses, some do not. So just so you know, if you submit your assignment late, it is considered that you've not submitted your assignment. So we might have to look into that. So if you submitted your assignment late, just assume your assignment is not received. And lastly, regarding the assignments, I don't know why some of you were using your hands to draw a graph. I still don't understand. Is it that you guys are not able to follow with the lab sessions, with the simulation sessions we used to have? Or is it that some of you don't know how to write a code? Because I found it very surprising that some will just go and start using the graph sheet with their pencil to draw. If somebody is raising their hands, what is it, Munirat? You have a question or what?
Yes, sir.
Yeah.
You're saying people that submit the assignment late,
Yeah,
but you said you extend the submission date to Monday,
yeah,
right?
yeah.
So
So when
as
is
of
Monday starting?
Monday starts in the morning at 12
Morning what time? 12 a.m., right?
o'clock.
So
Yeah.
if you submit after 12 a.m., is that before or after the deadline?
If you submit before 12 a.m. or after 12 a.m.,
After 12 a.m. Monday.
that's after Monday. That's after, not before.
So the class rep reached out to me and asked about the deadline, and I told him Sunday 11:59 p.m.
Sir?
Yeah, Sunday 11:59 p.m. so that you have, and somewhere even sending. I think I received an assignment yesterday around 5 p.m. Yesterday is Tuesday, right?
Yes. So I just want to know, because I just want to know who and who submitted late, so that maybe I did not fall in the category. That's why I raised up my answer.
I cannot remember the names, right? There are quite a number of you, but some submitted very late, and some were even submitting yesterday, and some were playing smart, telling me that they sent the email, and the email didn't go through.
Right.
Yeah. So I don't
So
know
you
how
know,
you
in
will send an
Nigeria,
email.
we have network issue.
So when you send
I
an
think,
email, it will not go through just
yes,
because
there
MTN
was a
doesn't like you.
lecturer there was a lecturer that sent an email to the
Hmm.
class rep, and he did not receive it. Up till the lecturer have to come to the class and said, I sent you an email. I did not receive anything. So
Okay. Yeah, so we might
sir,
have to
please
switch to the
just
app
consider for the first time.
for the first time.
You know,
You are
most of us have
pleading
not done
on
this
behalf of the
before.
latecomers. Yeah.
Yes, sir. Yes, sir. Just consider for the first time, then it will never happen again. I think we have on other assignments to submit, so we can do better, sir.
Yeah, somebody is laughing. I think he is one of those who submitted yesterday.
Probably, sir.
Yeah. I don't know how yesterday became Monday. I don't even know. Because I was considering, okay, those who submitted on Monday, I can overlook it, because maybe they do not understand that Monday begins at 12 a.m., so they think the whole day. But then somebody was sending the assignment yesterday, which is Tuesday, and around 5 p.m. I don't know. Okay. So, and most of you actually,
Just
yeah, you
consider us, sir.
tried. Most of you tried. However, I didn't get what I wanted, to be honest. It wasn't up to my expectation. I don't know if this is the first time you guys are doing assignments, writing it down in PDF format. I don't know. But the majority, I don't know. Have you not done any report before where you are expected to run some simulations and then report on your findings? No? Maybe. So I guess you have not. So I will send you the template, as I said. That could maybe serve as a reference
Guide.
point, yeah, and guide for
Okay.
the future submissions. Okay. When you are given
Okay,
an
sir.
assignment like that, by default, of course, you are expected to do some preambles, which I didn't indicate, which is fine. But by default, you generate some results. And when you generate the result, you tell people about the result and what the result is all about. It's not just generating the result and giving me, okay, because some didn't even go to that extent. Some just stopped by doing what they did with hand. The others who have at least tried, they came up with a Python code. I know also some of you copied, and that's something I can easily tell. There is no way two codes will be the same. There is no way two codes will be the same. No way. Every code is always going to be different, either from the way the engineer designs his functions or how he uses white spaces. And we all have our signatures. If I have my code, if you see my code, you will understand this is my code mostly. So if you copy directly from your friend, it's just something that can be easily identified. So I will send the template. You can use it as a guide, and we will see. The key thing is for you to understand what is it that you're supposed to do, because there has to be a project at the end of the day, and the project is going to be individual, unless if time doesn't permit, then it could be a group project. And I will send the topics for the project. So if you don't know how to do, like, you don't know how to code, I don't know if you will be able to do well in the project. I always prefer to give projects as my continuous assessment. I think it is better for the students. At the end of the day, when you graduate, nobody cares about your memory prowess, what you were able to memorize. If you want to be able to be tested and evaluated based on memory, maybe you should have gone to study law or study medicine. But an engineer, you are supposed to be a problem solver, not a memory or a memorization machine. That's not our job. Okay. So today we're going to look at per unit system, and I don't know. Let's see what we can do. Yeah. Per unit system, we were able to do some last week. You are able to revise your notes. You must have known what is it that we were trying to achieve. You have a transformer, you want to analyze a transformer. We have also seen how we can be able to figure out the values of components of a transformer, the losses how they can be represented electrically, and then how you can be able to determine the values for those components. So another method that you can do, apart from what we've done last week, is to use the per unit system. So in per unit system, what we normally do is to pick a quantity, and we also have another value or a quantity, which we call the base value. Then you pick a value and divide it by this base value, and that gives you quantity per unit. And there are so many reasons why we do this. First of all, it simplifies our computations. So calculations becomes a lot easier when you use a per unit system. You also and also in terms of complexity of the circuit, with the per unit system, you can easily determine the properties of the circuit and get some insights into what the circuit is all about. So we will take an example, okay? But by default, when you have a system, we're going to have what we call the base values, and you will also see the actual values and how the actual values can be translated into a per unit system. And there is no unit here, right? For example, voltage, if you divide it by a voltage, then you cancel out the volts. Ampere or current, if you divide it by a current base, then you have also no unit. So it's unitless. It doesn't have any unit. But what we can do is to use the PU or per unit to just show that, okay, this is a conversion from an actual value to a per unit quantity value. So, for example, we have apparent power, reactive power, and the real power. However, most of the time, we usually use two base quantities, okay? If you are given a system, you can pick some values from that system. Let's say a transformer circuit, you pick the source voltage and then the transformer power. This can serve, okay, this can serve as your base values, the voltage and the power. Okay, and of course, we are talking about the apparent powers. Since most of the transformers, you will see the rating is always in what? In kVA, right? Kilovolts ampere. So it's always the S, which is the apparent power, for example. So the impedance also can be defined as the base voltage divided by the base current. And you can also use the second relation, which is the V squared over what? Over P, right? That gives you R. So because P equals to what? V squared over R. So you can make the impedance the subject of the formula and you get V base squared over S base. We have also the admittance, which is just the inverse, okay, of the impedance, which is the I base over the V base. All right, so let's take a look at a quick example here. We have a transformer or a transformer circuit. Here we have two transformers, T1 and T2. T1 is a step up. Okay, for every 1 ton, the turns ratio in T1 is what? Is 1 over 10, right? It's 1 over 10. That's the turns ratio. NP over NS, so 0.1. For T2, the turns ratio is what? 20 over 1, which is what? 20. Okay, so this is a simple power system that has two transformers. We know that this generator that is generating the electricity is rated with 480 volts. Okay, the angle is 0 degrees. And we have IG, which comes out. Then we have the line, okay, which is the cable you connect to the load. The line has some internal properties that exhibit some resistance and inductance. And each one of them has its corresponding value. We have our I line that goes through the line. We have the second part, which is the region, the third part, sorry, which is the region 3. Here, you have a step-down transformer with a turns ratio of what? 20. Here in the region 3, that's where you connect the load. The load is what? 10 angle 30 ohms. And the current passing through the load, we can consider it to be I load. So we have a question here that we are supposed to find the base voltage, the current, impedance, and apparent power at every point in the power system. So we want to find here at, sorry, pen. So we want to find here, here, and here at every point what's the base voltage, the current, the impedance, and the apparent power. Okay. Then after that, we will get the equivalent circuit in the per unit. Okay. Then we will look at what power is supplied to the load. And lastly, what the amount of power that is being lost across the transmission line. So we're going to look at our resistance here and then multiply it by I squared as usual to get the loss. All right. So to start with the first one, we know that we said initially that when we are doing per unit system, we will pick two values always to serve at the base, which is always voltage and apparent power. So if you look at here, we are given the voltage to be 480 volts. And the generator, in fact, we are even given this, right? So we know 480 volts, 10 kilo volt ampere, 10 kVA. All right. So this serves as our reference, and it's going to serve as our base value. Using this base value, we can find the base current for the first region, this region, okay? Region 1. So what do? We said the base current in the first region can be divided by, can be determined by dividing the apparent power in the base region and then by the voltage. And keep in mind, this S base is going to remain constant throughout the circuit, okay? Throughout the circuit, our S base is going to remain constant at 10 kilovolt ampere, right? Because the generator has a power of 10 kVA. So we are going to retain 10 kVA to be constant. But as voltage moves, we're going to have voltage drops across. So the V is going to change, current is going to change, but the power remains. Okay. So if you remember, P equals to IV, right? So that means I equals to P over V. And the P here is the apparent power divided by the voltage, which we already know. So we know in the first region, the I base is what, 20.83 amps, okay, per unit. Z base, okay, using Ohm's law, right? So you can say V equals to IR, so that means impedance is V over I, right? So using Ohm's law. So what do you have? You know your V base is 480, and you've already obtained I base, so this gives you an impedance of 23.04 ohms. Now let's move to the second region. We know the turns ratio is 0.1 NP over NS, where NP is what, 1 and NS is 10. So we know it's 0.1. The voltage here is nothing but the voltage in the first region divided by the turns ratio. So we are going to step it up, right? We had 480 volts before. Now our voltage has been stepped up to 4,800 volts. Based on that, we know that S base, as I said, is going to remain constant, is 10 kVA. We can now determine the current in the second region to be also V over what? Sorry, S over V, where S is 10 kVA and V is 4.8 kilovolts. And that gives us 2.8083 amps. Using this, we can find the Z base with what? V over I. So V is 4,800 divided by I, which is 2.083. Now we know that in the second region, the impedance is 2,304 ohms. Okay, next is the third region where after the second transformer, the turns ratio there is 20. So V base 3 is nothing but V base 2 divided by A2, and that gives us 240 volts. So normally, of course, this is the voltage at the consumer unit always all the time. So 240 volts. So using this, keeping S base constant, we can find I base and we can find Z base accordingly. So now we know the power, the voltage, the current, and the impedance in each of our three regions, right? Region 1, region 2, and region 3, using the per unit system approach. Okay, so next is to see how we can convert this everything to per unit system, okay? So that you can say each component is given value in per unit. Starting with the voltage at the generator, VG, we know this to be what? 480. Then we can divide it by V base, okay, by V base 1, for example. So 480 angle 0 degrees divided by V base 1 gives you 1.0 angle 0 degrees. And as you can see here, we are in the per unit because V and V is going to cancel out. For the line transmission, which we already know, if you look at our line, 20 plus J60. And we know Z base 2 here, right? We obtained it. So we can divide Z line divided by Z base 2 to find it in per unit also, which is 20 plus J60. What is Z base 2? 2,304. This one here, Z base 2. When you do the division, we end up with this value in the per unit. Now moving on to the last region, the load. What is a Z load? So the Z load, we can also obtain it by dividing it, the value which is initially 10 angle 30 degrees. Then we divide it by Z base 3. What is Z base 3? Yeah, right, 5.76. That's Z base 3. So when we do this division, we end up with 1.736 angle 30 degrees per unit. And this gives us an equivalent circuit in the per unit as seen here. So this is VG, angle 1. We can see this is where our transformers were before. Now we have done away with them. And these are the values that we just computed in the per unit. Now that we know this, we also want to know what is this current. We know IG comes and then it goes in and come out I per unit. We want to find I per unit. So to do this, we can, if we know the total voltage in our source, which is V per unit, and we divide it by the total, the total load in the circuit. So our resistance or our impedance is connected in series, right? So if this is Z1, this is Z2, our Z total is what? Z1 plus Z2, right? So with that, we can do the summation. This is Z1, this is Z2 or ZL. You sum them up, and this gives you the current going through this circuit in per unit terms is given by 0.569 angle minus 30.6 degrees. We know current that is going through. So now what about the power? Okay, the per unit power. So if you look at that in the load, for example, you want to know what the load. In the load here, what the power, P load, in per unit terms. Since we know the current going is what, 0.569, okay, square it, and then multiply it by RPU. RPU, okay, how do you get RPU? If you look at this, this is 1.736 angle 30 degrees. You can convert this to Cartesian format. And if you do that, the real part is 1.503. Okay. So if you have 1.503, that's the real. So that is the R, right? So P equals to what? I squared R. We know the I, we multiply by the R, which is the real part of the impedance. And this gives us 0.487. That's the per unit. But if we want to get it, right, in its original value, for example, we can just multiply it by the S base. And then when you do that, you get 4.87 kilowatts. Sorry, kVA is supposed to be kVA, right? Okay. So you can see how our calculation has become a lot easier than if we were supposed to do the analysis like we did in the second or third class, I think. But now that we have things in per unit, our life has become a lot easier. And similarly, now, if we want to know what is the loss, the power that is lost in the transmission line, we can easily do I squared times R in the line. What is our R in the line? 0.087. So when you do this, the same I, 0.569 times 0.0087, we end up with what? 0.00282 per unit. So we multiply this power by the apparent power, and we end up with what? 28.2 watts. All right. Is that clear? Question? Any question? No question, yeah? Okay. So,
I have a question.
okay, what's your question?
Please, what's this S base?
That's the apparent power. And we have shown it in the beginning that S base equals to 10 kVA, right? Here. And what did I say? Always the apparent power remains constant, and this is given as the rating of the generator. Every generator comes with a rating. Okay, so the rating of this generator is that it is 480 volts and it has a power of 10 kVA. So you can maintain this, okay, throughout your calculation. That's why S base, you can see S base 1, S base 2, and S base 3 all remains 10 kVA. Any other question? No question. Okay, I hope it is clear though. So whenever you have a single device in your system, let's say transformer or motor, okay, so you use the ratings just like we did here as the basis for the per unit system. Just like here, we have a generator and we said the generator has 480 volts, right? 10 kVA at the rating, and we use these values at the basis for our per unit system. So always do that. And if the case you have, let's say, a lot of transformers in the system, then the bus voltage can vary, no problem. Or you can choose it arbitrarily. If you want to, you can say, okay, let me use something instead of 480 volts. So this is something to keep in mind. Okay. So if you have your units given in per unit, let's say with a different base, okay, and you want to convert them to another base. Let's say somebody in his S base, he picked 10 kVA, okay? Another one has his own S base, he uses 20 kVA. And just like we did in our previous example, right? We were using S base to be 10 kVA. So if somebody comes and wants to get values for the V and so on, but he wants to use a different S base, let's say 20 kVA, how can he do this conversion? So to do that, you can just easily take the first S base divided by the second S base, and whatever is the ratio, that gives you that quantity that you can multiply all through. Okay, so this is what this part is saying, that you can convert them, okay, using this approach. And you can use this formulation here, where we said, okay, the power, the real, the reactive, and the apparent powers can be given as, in one base, can be given as the same three other base, which is this is base 1, this is base 2. So we want to know the apparent power, the real power, okay, and the reactive power in this base where the S base is 20 kV. We can just take the real power or apparent power or the reactive power and multiply it by the ratio of the old base divided by our new base, and that gives us our PQOS in this new base. Okay. Similarly for the V, the voltage. So if somebody initially in our example, we use V base to be 480 volts, somebody maybe is using 240 volts. So we want to know, for example, okay, what's going to be the per unit base for a particular voltage. And this applies for when you have resistance, you know, you have also the impedance. You want to find this. Okay. How you can do it also is just to take that resistor's value, multiply it by the V squared of the first base and the apparent power of the first base, then divide it by the second base, which you are converting from. Okay, is this clear? It's a very simple thing. You are in base 1, for example, you want to move to base 2. Okay, and when you did your calculation in base 1, S base 1 is what? 10 kVA. And V base 1 equals to what? 480 volts. Well, the base 2 you want to use is different. V base 2 is what? 240 volts. And S base 2 is what? Is, let's say, 20 kVA. Okay? So if somebody tells you that the resistance I obtained when I was using this previous set is this value, let's say 10, for example, what's going to be the resistance now if I am now in this base? So let's say this is RB1. So what's going to be RB2? So what do? You just say, okay, where is the RB1? Okay, it's 10. Multiply it by V base 1, which is 480 squared, times 10 kVA, divided by the new one, which is 240 squared, times 20 kVA. And this gives you R base 2. Okay? So this is what we're talking about the conversion. Is that clear? Is that clear?
Yes, sir.
Okay. Just to make sure everybody is raising their hands. Okay, Omar, what the question? You have a question, Omar? Okay. So it's clear, I believe. All right, so now we have another example. We have a transformer, okay? 8,000 by 240 volts. So this is a step down. 20 kVA transformer. This is the core resistance and the inductance here. We know also the R equivalent and the X equivalent. So if you remember, our transformer circuit is like this, right? We have the resistance here. We have the inductance. Then we have R equivalent, something like this, right? So this is the R equivalent, X equivalent, RC, XM, if you do not forget, right? So this is the values. We have them here. And we want to convert the values of this transformer to per unit. Okay? We want to convert them to per unit. So in order to do this, we need to find, for example, the base impedance. Okay, we need to find this. And how do you find the base impedance? Remember, we know this. You can set this to be the S base. Okay, and we know 8,000, sorry, we can make it the V base. So if that is the case, what is the Z base 1? It's going to be V squared over S, right? Just like we did previously, which is 8,000 divided by 20,000, but the 8,000 is squared. And this gives us the Z base 1, which is 3,200 ohms. Now, we know that our RC, right, is 159, XM is 38.4, R equivalent is 38.3, and X equivalent is 192. So if we want to convert this part, these two, okay, let's call it Z equivalent, right? We want to convert it to per unit. What do? We add them up and divide them by the Z base. And that's what we did here at 38.3 plus J192 divided by the 3,200, 3,200. And what do you have? 0.02 J0.06 per unit. You can pick this RC as well and divide it, because this one now, okay, is a parallel connection, divided by the 3,200, and we get 49.7. With the impedance, okay, with the inductance, you can do the same. This is what, 38.4 kilo ohms. Okay, kilo ohms, you divide it by 32, and you end up with what, 12 per unit. So that means our circuit here, we can replace this RC with this value 49.7 per unit. XM, we can replace it with this 12 per unit. R equivalent plus what? X equivalent. So the R equivalent will be 0.012 and the X equivalent will be 0.06, okay, in per unit. And this is your circuit. Is that clear? So Is clear or not? Almost.
Not clear, sir.
It's not clear. Okay.
Yes.
Okay. So we said per unit system helps us to simplify our computation when we are doing analysis of transformer or electrical machine circuitry. Okay. So we are given a simple system here that has a transformer. Okay. And this transformer is rated to be 8,000 by 240 volts, 60 Hz, 20 kVA. This is the transformer rating. We also remember in our previous class, we discussed the losses within a transformer, right? We talk about the core losses, we talk about the copper losses, right? Talk about the core losses having hysteresis losses and eddy current losses. And we also have seen how you write the equivalent circuit of a transformer. And we said all those losses can be represented, right, electrically in a circuit where the core losses will be in two parts. Okay, RC and JXM. And then the line losses or the copper losses are those ones, right? So you have this. This is the equivalent circuit of a transformer. We discussed this last week. So if you have this, what they are telling you is that the RC is 159. So this is 159 kilo ohms. This is 38.4 kilo ohms. This is 38.3 ohms. This is what? 192 ohms. Okay? This is what we know. Okay? But we want to convert these values to per unit so that our our calculations and analysis becomes easier. So what do? We said, okay, let's pick something, always S and V, okay? Always. You have to pick an apparent power and call it S base, and you have to pick a voltage and call it V base. Okay? So when you have something like this, what do? You have to put S base to be 8,000 volts, 20 kVA, because it is there in the rating of the transformer. All you have to do is just to bring it here. And then also the V base is there in the rating of the transformer, 8,000 volts. Okay. So with this, if you want to convert these elements, RC, JXM, and these values here, you want to convert them to per unit, you can just get the impedance, which is the Z impedance. And to get the Z impedance is easy. You can first of all find the Z base. Z base is nothing but V over S, right? V squared over S. Ohm's law, right? P equals to what? V squared over R. So R equals to what? V squared over P. So that's exactly what we did. We found the Z base to be 3,200 ohms, which means our equivalent Z can be, which is this one, right? Z equivalent. You can pick it up, sum them together, and divide it by this Z base, and you get your Z equivalent in per unit terms. You can see this is simpler to write, 0.012, what have you. And you can do the same for RC and for XM by dividing the equivalent RC, which is 159 kilo ohms, divided by 3,200. This also same thing with the XM divided by 3,200. So this divided by this, you get 12. And then you can now replace those initial values of 159 with the 12, 38.4 with the 49.7, this with 0.012, and this with this one. Okay. Is that clear?
Yes.
All right. Any other question? Any other question?
No, sir.
Okay. All right, so let's look at voltage regulation and efficiency in a transformer. This is important because if your transformer is very efficient, then you're going to get value, right? For the money you paid. Okay, so when you look at transformer, our real transformer, you know the circuit of a real transformer as you know it, right? The core losses, and then the line losses or the copper losses, which we have. The copper losses, that's our transformer. So we have what we call full load voltage regulation, VR. Okay. What? Is somebody saying something?
Ta yi kyau. Kwaban maza dai daban take.
Yes, somebody is making noise.
Ka gani?
Okay. So here we want to, for example, obtain a quantity called full load voltage regulation, okay, VR. And we do this so that we can compare transformers, okay, to know which transformer is more efficient. If you have like two transformers and one is more efficient, you want to pick the one that has the better efficiency. So how you can be able to know is to say, okay, let's calculate the full load voltage regulation of each transformer. To do that, you can use this equation here. VR equals to VSNL minus VSFL divided by the VSFL. And this will give you the value, okay, of the full load voltage regulation, where this VSNL is in the secondary no load. So at the secondary, remember, if you have your transformer, at the secondary, this is where you put a load, right? L. So if you have no load, okay, what's the voltage when this is not there? And then when there is load, when there is full load, what's the voltage? Okay. So the key thing is here, we want to say that if, for example, let's say the VSNL, where when there is no load, is 100 volts. And when there is full load, we see 80 volts. And then we divide this by 80, right? So this is what? 100 minus 80, 20 over 80. What does that give you? That gives you 25%, right? 1 over 4. Okay, because you multiply by 100%. Then you have another transformer at full load, it is what? 100. At no load, sorry. But at full load, we are seeing 10. Okay, so this is also 10. So this is 90, for example, divided by 10. The difference, sorry, yeah. So what do you have here? At full load is supposed to be more, for example. So this is, let's say, 9 times 1000. So this is 900%, which is Okay. So what happens at 50? You have 100 minus 50 divided by 50, right? And this is actually what you always are aiming for, to get 100%. This is an extreme case which you do not have. So this is what we normally do. Okay, we always want to compare two transformers and we want to know which one is better. So how do you do that? You try it with no load and you try it with full load to find the voltages. And based on that, you come up with your conclusion that, okay, let's take this transformer, it is more efficient. Okay, so we have also this, if you have, for example, your equivalent circuit. Okay, and you refer it to the secondary side. That means your RC here, you divide it by A squared, and XM here, you divide it by A squared, if you are referring to the secondary side. So if you have voltage here, which also you divide it by the turns ratio, you can be able to find it using Kirchhoff's voltage law, right? VP over A is equals to VS plus R equivalent IS plus J equivalent IS. Yeah, this should be clear, right? Here, the voltage across this side here, right, is VP over A. And if you do the Kirchhoff, right, you go like, say, clockwise like this. Okay, you have IS multiplying this, IS multiplying this, and you have VS, right, going in this direction. So according to Kirchhoff's law, we can sum them up. And the summation of this voltage here, all the drops, is going to give you the same thing that is across here in the parallel. I hope you didn't forget your KCL and KVL. Okay, so if you have, now we're going to go into phases. So sometimes if you have your transformer and you want to get these values, you can use either the open circuit or the short circuit like we discussed before and get the equivalent values, or you can use the per unit system to get these values. And then you can now come and draw the phasor diagram like we discussed earlier, where we know that, for example, in the phasor diagram, if you have a transformer that is what? Operating at a lagging power factor, then you will see that the VP over A is greater than the VS, and the VR, okay, the voltage regulation is also greater than 0. Okay, so at a unity power factor, that is to say, if psi is what? Equals to 1. So that's unity, if psi is 0, so cos 0 is what? 1, right? So if this happens to be the case, we will see that VR is greater than 0. However, if the transformer is operating at what? At a leading power factor, where the secondary current is leading, okay, IS is leading, the secondary voltage can be higher than the required primary voltage. So VR is what? It's less than 0. And for that, we know the efficiency of the transformer is given by the output or by input, right? This is common for every system. To obtain the efficiency, you just divide the output by the corresponding input. And this gives you this equation, where the P input is whatever is outputted plus whatever is lost along the way due to either copper losses or core losses. So when we know this, we know the efficiency of the transformer, where P loss is from either copper losses, eddy current losses, and hysteresis loss, with these guys giving us what we call the core loss, right? The core loss, which we discussed. The output of the transformer is very easy. It's given by the voltage, the secondary, the current in the secondary, then multiply by the power factor in the secondary. So if you substitute P with this, P out with this value, you end up with what? Efficiency equals to VSIS cos psi S divided by P out, which is also the same VSIS cos theta S, plus the copper loss and the core loss. This gives you the efficiency. Is that clear? Yeah, Omar, what's your question? You raised your hand. What's your question? No question.
Sir, please, I wanted to know where we are getting the copper loss.
You don't know where we are getting the copper loss. Were you here during our lecture 4, I think? You watched the video and you were attended the session?
No, sir.
So that's why you don't know. So I will encourage you to go and watch the video, okay? Copper loss is due to the winding. You have windings in a transformer, right? Windings are made from cable, the ones you always see in a transformer, those windings. Copper, right? The cables are made of copper. So due to that winding, you end up with some losses in your circuit. You don't have a perfect wire that everything you send to it, it takes it and pass it across. Copper is one of the best conductors we have that has the lowest loss. That's why we are using it for electrical systems. Okay? So that's where the copper loss comes from. So the transformer has that loss due to the windings, and the core loss is because of the frame of the transformer, the metal frame, which you wind the wire, the cable, right, on it. So that is the that one also will lead to what we have, the leakage flux, which we discussed before. That brings about the core losses. We discussed this in details in our previous session. So go and watch the previous session. You have the recording, or you can read the material. Is that clear? Okay, so let's look at an example here. We have a 15 kVA transformer with 230 volts, 2300 and 230 volts, okay? Okay. So this is also what step down. Okay, so they use open circuit and closed circuit tests to determine those values. We have discussed this in our previous session, that way how do you do open circuit and how do you do closed circuit. And when they do the test, they have the readings as you've seen here. So the first question is asking us to find the equivalent circuit of this transformer referred to the high voltage side, which is the primary, right? That's the high voltage side, the primary. Okay, so we are going to refer things to the primary. And then also do the same, refer it to what the low voltage side, which is the secondary. And we have also done something like this before. You have seen how you do referral to the primary and to the secondary. Then calculate the full load voltage regulation. Now the VR, which we just finished discussing, when the power factor is what lagging and is 0.8. And what do we say when VR is, when there is a lagging power factor, VR is greater than 0. So we want to know it. Okay. We have also another 1.0, which is the perfect. And then there is also the VR 0.8, which is going to give us less than 0. So we're going to do this calculation. And then next is to plot the voltage regulation as load is increased, okay, from no load to full load. So we want to see this transformer, how will it behave? We have no load on it. Then we start to add some load. We keep adding until when it is at full load. Okay. And then we want to see at different power factors, 0.8 to 1.0 and 0.8 leading and lagging. And lastly, we want to find the efficiency of this transformer at full load with a power factor of 0.8 lagging. All right. Is that clear? Is that clear? Okay.
Yes, sir.
So from our previous session, we know how to find what? RC, XM, R equivalent, and X equivalent, right? If we have this, you can go and refer back to your previous note. Given these values here, you should be able to obtain these values. We have shown it in our last session. Okay, so the first thing is to find always the excitation branch. We want to know the power factor, which the angle here is what, 84 degrees, because we know the open circuit power. We know the voltage open circuit from our experiment. We know the I open circuit. Multiply, putting everything here gives us what, 84 degrees. Excitation admissions, if you did not forget, YE is what? IOC, VOC angle minus theta OC, right? We have done this, and this gives us these values. If you do the conversion to Cartesian, you end up with this. And what is RC? RC, we say, is one over the real part. Okay, this is like we talked about this conductance last time. So I hope you guys are revising. So this RC will be the reciprocal of the real part, and XM will be the reciprocal of the imaginary part. So we know our RC, we know our XC. Same thing, we can use the short circuit test to understand this so that we can find the Z equivalent, right? Which is the composed of what? R equivalent and X equivalent. So we have find this part, we are happy. We have also find this part, we are happy. Now what remains is these two. So to find these two, just like what we did in our previous session, we find the theta SC and then we find the ZSE, which is just the VSC divided by ISC. And this we have them from the table. You go to the table, you find them, plug in this angle degree, and you find the real and the imaginary. So this arc EQ is the real, and this one is the imaginary part. Is that clear? So this is referring to the primary, the high voltage side. Okay. Now that we have it in this case, we want to refer this circuit as it is to the secondary side. We want to refer it to the secondary side. And when you are referring to the secondary side, what do? You can divide this by A squared, right? What is A? A is NP over NS, right? And is also VP over VS. We know our VP is 23,000 or to 2,300, and then the VS is 230. So this is 10. So A is equals to 10. So that means, let's see, what's A? Yeah. So secondary is 230, primary is 2300. So A is the VP over VS, right? But if you are going to the secondary side, okay, so what do you have is also the same. So this is A squared is what? 100, right? So that means if we refer this to the secondary side, what does it become? It's 105 kilo ohms divided by 100. So this is 105,000. Remove the 2 and you end up with 10,000, 1,050 ohms. Okay. Same thing for this one, 11 kilo ohms divided by 100, you end up with what? 110 ohms. Okay, this is the XM. Okay, this is the R. We are now referring it to the secondary side. Okay. For these guys, 4.45 divided by A squared becomes 0.045. Similarly, for this one becomes 0.0645. Okay, is that clear? Question?
Let's move on.
No question. Okay. So the next question is asking us to find the full load current on the side of the transformer, right? Okay, that's the next question. Calculate the full load voltage regulation at 0.8 lagging, 0.8 leading, and 1.0 power factors. Okay, so let's start looking for the VR. Okay, for that, we can get the full load current. Because remember, what is VR? Is V no load in the secondary minus V full load in the secondary, right? Divided by V full load. So to understand V full load, if we know, for example, the Z, we can, if we know the I, we can be able to know what is the current that is passing in the secondary. And to do that, we know our transformer is 15 kVA. So we divide this 15 kVA by our VS rated, which is 230, right? Because our transformer is 2300 by 230. So this 230 is here, and this one is given as what, 15 kVA. So we know the current that is in the secondary, which is what, 65.2 amps. Now using the Kirchhoff's law, we said that VP over A equals to what, VS. Then we now have this part also. Okay, so you can put this into the equation and you will be able to find the IS, right? So at PF, which is lagging, okay, your IS is equals to 65.2 angle here, 0.8, okay? So cos inverse, because we know power factor is cos psi, right? And we say it's 0.8. So what the angle? So cos inverse of 0.8. So 65.2 cos inverse of this gives us what, 65.2 angle minus 36.9 degrees amperes. Okay, now we know the current going here. So now we know IS, we can put it into this to find VP over A, for example. And what is this? Okay, so VS is this. R equivalent, we know it. IS, we know it. J equivalent, IS, we know it. And this gives us 23.4.85. Okay. So if you look at our equation for this one, we said the V no load is nothing but VP over A, the magnitude. And the magnitude here is at 234.85 minus 230, which is this that we already know, divided by 230. VR here is what, 2.1%. And as you can see, VR is greater than 0. Our power factor is positive. Sorry, it's lagging, not positive. Our power factor is lagging. So our VR is what? 2.1%, which is greater than 0. When our power factor is 1, okay, so that means here cos inverse of 1, right, which is 0, so angle 0, so 65.2. That's our current. So you plug into the same equation using the Kirchhoff's equation, and you get the VP over A to be 23.294. Now the voltage regulation, the resulting voltage regulation is just VP over A, which is this, minus VSF, which is 230, divided by 230, and you end up with what? 1.28%. Okay. You can draw the phasor diagram. We've discussed how to do that. You can draw your Cartesian, for example, and you come and say, okay, assuming this is the origin, okay, IS and V, they are in the same direction, right? So if you take some scale, this is 65, and this is 230 up to here, for example, 230, okay? So this gives you your current, okay? And then you can get VP over A, which is this, 232, angle 1.04, can draw it in the quotation, you will see it is going to give you this. So from the phasor diagram, you can see that you have two values, this one and this one. Okay. And each one is giving you some information regarding the losses. The next thing is at leading. When this is leading. Okay, so what happens? You can plug in the results, and you can see our VP over A is 229.85. When you substitute this here, you end up with a negative. You end up with a negative, the voltage regulation. So if you have different load currents, if you have different load factors, just keep using the same equations and just keep changing the load factors or changing the current. And then you will be able to understand what is the VR for that particular transformer. Is that clear? The final question is asking us to find the efficiency of the transformer. And we know efficiency is P out over P in, right? And we say P in is what? P out plus P losses. Okay. So let's do the P losses first. The P losses come in two shapes. We have the copper loss and the core loss, right? For the copper loss is the I squared by the R equivalent, and this gives us 189 watts. For the core losses, we are V squared, VP over A squared divided by RC, you know, because the core loss are the first, these guys, right? So we want to know the voltage across this guy is VP over A. So since we know the voltage, we can be able to know the loss due to this element here. And this gives us what? 52.5 watts. For P out is simple. We know the VS, which is 230. We know our IS, which we calculated. Of course, assuming the lagging power factor, right? So what do we have? We have 12,000 watts. So that means efficiency is 12,000 divided by 12,000 plus all of these guys, and you have 98.03%. Okay, so this tells us how efficient our transformer is. Quite efficient, right? The losses are nothing compared to the output. Is that clear? Questions? Somebody is playing recording during the session. Somebody is watching recording of our previous session during the class. Somebody was playing recording during the session. Question?
Sir, I think the last class, we didn't have this in the slide. That's lecture 5.
No, I sent it, right? The annotated one.
Okay.
But I will send it
Please,
again.
okay, thank you. We hope to see this one immediately.
Okay. No question. Are we guys clear?
We'll look into it later and check. If there's question, we can bring it tomorrow, inshallah.
Okay then. For those who do not understand, read the lesson note, watch the recording. Okay, if you have questions, you can ask it tomorrow before we start the new session. Okay? Yeah.
So we're going to conduct like the experiment practically.
If what?
We're going to conduct like self-cited test or open-cited practically.
Okay, can you type your question because there is an echo from your end and it's not clear what you are saying.
Hello, sir. Can you hear me?
Okay, now it's better.
Okay, so what if like you want to conduct the experiment practically? Like on
You
a
want to conduct the experiments practically, okay?
Okay, is there like a way that you can do it?
So what experiment do you want to conduct? To know the efficiency of the transformer?
Oh yeah, or to get the parameters like the
yeah. So
XM
we discussed this last class, right? How you get this? Yeah. How do you conduct open circuit test and how do you conduct short circuit test so that you end up with these values, right? We did this last class. And when you get these values, you can use them to determine the component values, the values of the components, RC, XM, R equivalent, and X equivalent. We did this in the last class. Okay? So how do you do it? You guys are going to do this in the project. So you're going to design a transformer. Okay, you're going to simulate, get the base design. I will give you some parameters. As an engineer, you are supposed to design a transformer. Maybe I give you my budget. This is what I have. And I want it to be as efficient as possible. You have to prove to me that your transformer is the best efficiency I can get with the given amount of money I give you. And it will be able to satisfy my load characteristics, how much power I want. I'm going to give you all these details. So you're supposed to design. You're going to design the transformer, okay? You simulate it, you design it. And then maybe we can also construct it because they have, it's very simple. You get to construct the transformer, it's simple. You get the copper cable, you get the core, and you go and do it. Then when you finish, you go to the lab. We have a lab, right? We have power lab, machines lab. Any of these two you can go. They will give you ammeter, they give you voltmeter and the wattmeter. you can be able to conduct the open circuit test and the short circuit test just like we discussed in the class. Once you do that, you get these values here. Once you get these values, then I want you to recall those RCs, you know, find them, evaluate what is the RCs and what have you. Okay? So when you do that, of course, at the end of the day, you know all this, you can be able to obtain your efficiency of the transformer. Almost everything we've discussed so far is very straightforward. But if you do not understand the previous session or you do not refer back to them, of course, you will be lost. Because I'm not going to go back and teach you how to do open circuit and short circuit test and how to obtain RCs and R equivalent and what have you. We've already discussed that, and you have the recording, you have the lecture note, whatever. So that should be clear. Is that clear, Bilal? That's how you conduct the experiment. Go and read that open circuit and short circuit test in the previous lecture note. Okay, it was made very clear.
Okay, thank you, sir.
All right. Any other question? Because you can see the reason why we did dot open circuit so that we can be able to compute our efficiency of the transformer. Okay, Emmanuel, what's your question? Emmanuel, you are raising your hand, right? What's your question? Okay, I guess he has no question. Okay, guys, since there are no questions, we're going to stop here. All right. See you tomorrow.
Okay, sure.
Okay, take care. Bye.